Okay, guys, we'll pass back the quizzes at halftime. Grades were fairly low on that. Hopefully by the time the test comes around, you're doing a little bit better. Test on Wednesday. Test will be then returned on Thursday, which is our last day of regular class. We'll finish up the substitution blue handout, and then we'll move quickly into the elimination green. Question? Today and tomorrow is your group lab. Is due the TLC when you come to lab Wednesday, Thursday. And then Wednesday, Thursday, we're doing the double E2 elimination before you leave lab.
Extra elimination.
Extra elimination. Green? We'll have to clarify some of that, but whatever's due will be turned in before you leave lab. Okay, guys, good morning to you all. Let's get started. Any questions? Any other questions? Yes, I apologize for not being here at 8:30. My alarm was on weekend time, which means it didn't go off until I was about to leave the house. So I just forgot about you. Otherwise, I would have been here.
Did you get the green sheet that Hydrilla got last week? You said you wanted you to grab it.
I didn't get a green sheet. Anybody else not get one? Anybody else not get a green? Okay, let's see where we left off at with substitution. Y'all guys did a little studying at 8:30 this morning? 8:30 to 9? Anything at all? Group studying? Okay, I sent out answers to these here. We can do the first four real quickly, if you had questions about them. I don't know if we did this one in class or not. We have a tetrahedral carbon with a leaving group. We have a weak nucleophile. Can this be SN2? SN2 requires strong nucleophile, not SN2. So what is it? SN1. Well, for now, because on the next sheet we're going to introduce the possibility of doing elimination. Okay. So we can think more broadly here. Is this reaction going to be unimolecular or bimolecular? SN1 is unimolecular. Broader thinking. Yes, unimolecular because the nucleophile slash base, we might call it base a little bit, weak. Okay, all you know is SN1 right now, product. Substitution by SN1, what's going to be the product? What's the nucleophile? OH? That's because eventually it had to lose an H to go neutral. Okay? What's going to be the stereochemistry at this carbon? Going to be racemic. Because mechanistically, what does the water attack? Water attacks carbocation. Carbocation attacks from either side. So we end up with racemic. Yeah? We can just draw that something like this, with a star indicating racemic. Okay, how about this one over here? Carbon with a leaving group. By the way, what else is formed here if you totally show everything? HBr. Over here, product. Mechanism. Unimolecular or bimolecular? Why? Strong nucleophile. It's going to stick its nose in there. It's not going to wait for any ionization. It's going to be involved, and if this is involved, it's going to be SN2. Or later, E2. Bimolecular. Bimolecular means what? Concerted backside attack. Product here would be yep, inversion. Keep the backbone the same, you can show inversion just by switching bold to dash. Unimolecular, bimolecular. Unimolecular, SN1, ionization, product here. Boom, boom, boom. Carbocation from ionization. What attacks carbocation? Nucleophile, methanol. Oxygen loses an H. I- can take the H, we make HI. It's going to be stereochemistry here. Racemic. Is it going to rearrange? Is this carbocation going to rearrange? And you can move here. It's got to be careful that it moves here. You wouldn't show an arrow showing the arrow, the positive move there. The hydride can move there, leaving the charge here. It would be the same thing. It would go from secondary to secondary. I mean, does that? There's really no rearrangement possible here. Racemic, you get this ether because methanol attacked, and when you lose the H, you have the. Okay, the one on the right. Bimolecular, unimolecular.
I mean, bi.
Bi, strong nucleophile, bimolecular. So, what's the product? Well, hold on. Can you, SN2, bimolecular substitution. Can you do SN2 with this substrate? No, you don't do SN2 with a tertiary halide, or more generally, even the leaving groups on tertiary carbon. So, it's got to be bimolecular, but it can't be SN2. So, what do you do? Do you do SN1 instead? No, we said bimolecular. This guy's a bully. That's because this is going to be, yes, bimolecular, but it won't be SN2, it will be E2. This can take us into the elimination handout. Okay, the key below was supplied. Any questions about the ones below at this point? No? A little bit surprising there's no questions about those. All those look good?
On the very bottom, why is it NH2CH3 and not NHCH3?
I didn't quite hear you.
Why is it NH2CH3 as
Hold on,
opposed
NH2CH, methylamine instead of
to NHCH3?
the anion? NH2CH3 instead of the anion?
Yes, sir.
But why does it need to be that? Can it not be this? This is an sp3 nitrogen, so in the neutral state, it's a good nucleophile. You don't really need the anion. That's a strong nucleophile. Strong nucleophiles, anions, sp3, sp2 nitrogens. So here the neutral is a strong nucleophile. That'd be kind of overkill. Just not really needed. It's like killing a mosquito with a bazooka. Okay. Just not needed. Other questions? Okay, let's look on the back real quick. Another example of a drug synthesis using an SN2. Right here, starting with compound 42. And they're going to 43. It's a two-step process. The second step we really don't know. The second step, they're cleaving this group off over here to make it NH. They actually had it there, so at the beginning, only one nitrogen is nucleophilic. Can you tell which is nucleophilic? Which one is a good nucleophile? On the left, the lone pair is in sp3. This lone pair is in a doing resonance, p orbital. So they have this ester here to make this non-nucleophilic, so it won't react on both ends. Then the second step removes the ester and reveals the amine again. The first step is boom. This comes in here and that's a strong nucleophile, yeah? Bimolecular, SN2, concerted backside attack. Kick off the bromine. Something's going to take an H. Why do you think they include sodium carbonate in the reaction? Something to take the H. Okay, the H is now gone. And then the second step removes the ester. Don't worry about that. First step is a good old SN2. Purpose of the base we know. Can you do SN2 with this halide, with this leaving group compound? What is it? Primary, secondary, tertiary? It's secondary. Can you do SN2 with secondary? Yes. Okay, I say SN2 most likely. How can we confirm that it's SN2? Beyond just our sort of good theoretical assessment. Would you like more proof? How would you confirm it was SN2? Why does it matter? Anybody know how you would confirm this?
Look for the inversion.
Look for what?
Inversion.
You can look for inversion. Problem is, this is not chiral. Well, actually it is chiral, because the chlorine up here. That is chiral, but there's no stereochemistry shown. You could do it with stereochemistry. You'd have to get a starting material that had RS. Yeah, you could look for inversion. If you got inversion, you know it's SN2. If your product ended up being racemic, then SN1, cation, carbocation chemistry. What's another way to tell?
See if you have a strong nucleophile.
Do what?
Look at the nucleophile and see if it's strong.
Well, that's part of the problem. That's more of a theoretical. I called it strong. But is it really strong? Is it, because sometimes these statements are just theoretical statements that work 95% of the time. What if this is a case where 5%? We're looking for some more actual experimental proof. Also, it's neutral. Now we said neutral amine is strong. Yeah, but it's neutral. So that is my theoretical statement really holding true? How can we prove it with some experimental evidence?
From resonance,
Resonance?
if it's available.
What do you mean resonance?
Doing it after the ship and moving the
I mean, if your product underwent some type of rearrangement, then clearly it involved cation, clearly that would be SN1. But there's no rearrangement in going here. That doesn't mean it still couldn't be a carbocation and then you attack it and do SN1 without rearrangement.
Look at the rate.
Ah! Rate. Okay, explain. How would you create an experiment to answer this question?
You increase the concentration of both reagents to see if that would affect the rate.
Yes, you can change the concentration. Well, we know SN1, SN2, this is involved in the concentration of both of them, or the rate of both of them. This guy, what if you double the concentration of this and the rate does not change? What does that tell you? SN1. What if you double the concentration of this and the rate doubles? There you go, you could do rate. Okay, why does it matter? Well, what if you worked for this drug company, they paid you good money, and they wanted to improve increase the rate of this reaction. Currently, when you come to work for them, they do it in 10 hours. But they want it done in 2 hours. Well, then you say, well, let's increase the concentration of this reactant, because you make more concentrated reactants are going to come together. Maybe react faster. Well, that's fine and dandy if it's SN2. But if it's SN1, you can increase the concentration of this all you want. And you ain't going to increase the rate. So if it's actually SN1 and you spend a lot of money in doing this and you don't have any difference in outcome, you may not have a job. You wasted the money. Because you didn't first confirm that this was SN2. Make sense? On the sheet there's 3 SN2 reactions, each one hand labeled. Okay, elimination. I kind of wanted to go over them in the lab. Do you have 3 assigned? I can tell you. The top compound belongs to which spectrum? Of the spectrum 1, 2, and 3, the top compound belongs to which spectrum? Correct. Correct. The middle compound goes with which one? Middle. Correct. The other compound, which is the third compound, goes with the first spectrum. Yeah. Correct. It's the opposite. First compound, bottom spectrum. Middle compound, middle spectrum. Third compound, first spectrum. Is the answer there. We'll go over those in the lab lecture this afternoon and tomorrow afternoon. Okay, elimination. There's an example here on a warm-up sheet. There's an E2 elimination here. We take this compound. We can eliminate HI. And H is removed, and I is removed, and we make an alkene. 2 or 3 weeks ago, we were doing addition reactions of alkenes. And we could have made something like this. That is, this way is minus HI. Well, a couple of weeks ago, we were doing these reactions. Having an alkene and adding like HI. And making like an alkyl iodide. Addition. Elimination reactions is a way to make alkenes. But we don't study it when we do alkene chemistry because that's different chemistry. Eliminations go hand in hand with substitutions. Because when you do an elimination, you have a leaving group just like a substitution. And there are 2 mechanisms when you do elimination. One's called E1 and one's called E2. General line reaction. Set up just like the first page of the SN2 handout was set up for the SN1, SN2. We have a tetrahedral carbon with a leaving group. Tetrahedral carbon, right? We're going to have some type of base. Now with the substitution, we call this a nucleophile. And the only difference between a nucleophile and a base typically is base attacks an H, nucleophile attacks anything else. So So they're very similar. Although we do know that sterics affects nucleophile much more than base. Okay. Beta elimination. The beta refers to not the leaving group part, but the H that's removed. Look at this reaction when H is removed. And from the leaving group, the first carbon is alpha, and the second carbon is beta. We're eliminating an H from the beta carbon. So this is often also just generically called beta elimination. What's going on here? The X group is just left. It takes on a lone pair when it does. Perhaps a charge. What do you call something that leaves? Leaving group. Okay, the X is a leaving group. Same leaving group discussion applies here. Iodine's a better leaving group than bromine. Tosylate's a great leaving group. OH is only a good leaving group if you're protonated. So all that still applies. What ends up taking the H, bonding to the H? The base. Makes sense. There's a generic reaction. Okay. This reaction can also be called, what have we removed up here if X is a halogen? We removed HX. Now we didn't create HX, but that's essentially what we removed. And X is often being halogen. If X is a halogen, this is also called a dehydrohalogenation reaction. D, we removed a hydrogen and a halogen. So there's a term, a big long word for you. Dehydrohalogenation, when you eliminate HX from a molecule, typically to give an alkene. Okay, let's look at a specific example. You take this alkyl bromide, this base. We can do a beta elimination. Get the alkene plus the leaving group, now the base has the H. Possible mechanisms for this. Just like on the substitution, we did two possible mechanisms and then we said which one is best. Okay? Leaving group's got to leave. Well, what if it's just left? Can a leaving group just leave? Sure, but it kind of depends on what you're going to be making. You're going to be making that plus what? If that ionized, it would give that. Okay, are you liking this mechanism so far? What did we form? Primary cation. Good? Bad. So already, maybe this is not the actual mechanism. But I am going to do an E1. And the first step of an E1 is the same as the first step of an SN1. Ionization to make carbocation. There's your Br minus. Okay? What's next? You got two H's here. At this point, the base, also this is a cation. If this thing loses H+, we can show, first off, if it loses an H, now we have the same formula as this. If it loses the plus, well, then it goes to neutral. And that would be it. So it needs to lose H+. Okay? There's no H+ sitting here, but the base can now take one of the beta hydrogens, bond to it. These electrons, here we go. What do they need to do to get the final product? They need to, these two electrons need to fall in here and make pi bond. If they do that, we're done, right? Okay, which step looks like the rate determining step? Ionization, it's just like SN1. First step is the rate determining step. The base taking the H is thus called the Now we can also just call this step beta elimination instead of the overall. That's getting very specific because in this fast step we're removing the beta hydrogen. What did we do in the first step? Ionization. Okay? If you did a reaction coordinate diagram, you would have how many intermediates? 1. Carbocation. And forming it would be the rate determining step. Then when you form your product, you're falling back downhill. That's going to be fast. Which step is the base involved in? Is the base involved in the rate determining step? No, it's not. Of your two substrates, how many are involved in the rate determining step? Only one. This is an elimination unimolecular. E1. This is not the mechanism for the example reaction. Two main reasons. First off, you don't want to make the primary cation. Bad. You'd rather make tertiary. What's the second reason? The second reason is this guy is strong. It's an anion. Is the strong going to sit back and let this ionize? No, it's not. We'll see below what's going to happen instead. If you've got a strong nucleophile and you're doing substitution, mechanism is going to be SN2. Because the strong nucleophile is going to come in and do something. Same thing for this. If you've got a strong base, it's going to be E2. Question?
Why do you have two arrows going from the base to the intermediate?
Coming from the base to...
Yeah.
I only have one arrow coming from the base to the intermediate.
Oh, I thought you just erased one, so I thought there was two.
Well, that's just the progression arrow. We went from there to here.
Okay.
And it had RDS written there. There's two arrows here because when the base take the H, these electrons move in. So these two arrows are concerted. Okay, what's another way to do this? What's another way to do this? Now, I'll give you a big hint here. Concerted. What's another way to do this? Here we go. These electrons attack H, these electrons move in, and these electrons kick up. All concerted now. All this happens at the same exact time. One transition state. Transition state, this bond is forming, this bond is breaking, that bond is breaking. Or, well, this bond is breaking, that bond is forming, all at the same time. What does that arrow movement give? What does this arrow movement give? Yes. There you go. There's your mechanism. Is it not? This is making the bond to H. There it is on the far end. What does this arrow mean to you? These electrons are moving in to make pi bond. There it is here. What does this arrow mean to you? It's getting kicked off. The bond is breaking and is becoming another lone pair. Leaving group takes on a lone pair, just like we said at the top. But that is a minus charge. There you go. All concerted now. Okay, which step is the rate determining step?
The only step.
The only step. So, which of these are involved in the rate determining step?
Both
Both
of them.
of them. E2. There's your E2. It's a concerted beta elimination all at the same time. Which mechanism do you like better for the example reaction?
E2.
Yes, the example reaction is E2. Mainly, like we said, we don't want to make primary cation. Why would this want to take this H? It requires a little bit of thinking there. Is there another possible mechanism for this reaction? Could you show this another way? Bond here?
Yeah.
But there's no oxygen-carbon bond down there. Unless you do that and then do something else. Here we go. Here's another possible mechanism. What if this took the H and these electrons just stayed here? Like a good old acid-base reaction. What would that give? What is this, the hatch or something? If the base just took an H, left the electrons behind, that's a good old classical acid-base reaction. Yeah? We could have did this 3 weeks ago. I mean, is this different from what we did above? Did we do this above? No, we did not. We never made an anion above. Then this could, how could we, so there's that. There's one of your products. How do we get the other two? This could then do what? Move in here and kick that off? Okay. Is that mechanism different from the two above? Yes. There's another way you could possibly do it. In the first mechanism, what type of ion did we make? Carbocation. In the second mechanism, what type of ion did we make as intermediate? None. In the third mechanism, what type of ion did we make as intermediate? Anion, carbanion. This is not the mechanism either. Mainly because that carbon is not acidic. Carbanion is very hard to form, not going to do that. So it's a unique concerted. Now most books don't show this. The reason I show it is because sometimes you guys want to do this. We do not make carbanion here. Now there's actually a reaction organic 2 where you might do this. But not here. Let me ask you this. In E1, is the base involved in the rate determining step? No, this is not the question I want to ask, sorry, because that's going to be different. Here's the question. In E1, is the compound with the bromine involved in the rate determining step?
Yes.
Yes, it ionizes. That's the rate determining step. How about E2?
Yes.
It's only one step. It better be involved in it. What about this? What looks like the rate determining step here? Making the ion. Here, the leaving group leaves in the fast step. That's a huge difference in this. Because the leaving group leaving is going to go back downhill to your neutral compound. Okay. This third mechanism I will never show again. And hopefully you will not either. But the reason I show it is because a lot of times you guys draw something like this. This is not involved in our E1 or E2. But hopefully you do understand that in this third one, the leaving group leaves in the fast step, which is different from E1, E2. Okay, another example here. If you take this compound, this 2-bromobutane, and heat it with tert-butanol, or no solvent at all, if you just heat this compound, you can get this alkene plus HBr. Mechanism, is it E1 or E2? E2, just like SN2, requires a strong nucleophile or base. Since we're focusing on elimination, we'll call it base. Is this a strong base? No, it's not an anion or an sp3, sp2 nitrogen. Not a strong base. So you can't do E2. So this mechanism is E1. That is, this guy's weak. It's not going to come in here and take the H and do all that. It's too weak. Won't do anything. Lazy. Just sitting on the sofa. The only thing that can happen here, you heat it up, this thing can just ionize. Boom, boom, boom. Just ionize. Now, how do we get home? Something's going to take the beta hydrogen in a fast beta elimination, put the double bond in. What can take the H? Well, if I'm showing HBr, this can take the H. And if it does, then what did this do at all? Well, maybe it just served as solvent. By the way, remember conformations? This has free rotation. These groups are kind of sin. They're eclipsed, sin. Is that the best conformation? Or will this thing want to rotate? Yeah, what if it rotates? And we get boom, boom, something like this. Which is favored? This is favored. Okay? Br minus takes a beta hydrogen. These electrons move in here. What do we get? We get that. These groups are anti in the most favored conformation. They're anti here. Trans. Plus HBr. What mechanism did we do here? E1, carbocation chemistry. Using a weak base. Or really no base at all. I mean, but that could have served as a base. For example, this is just like water. And if we had water, a lot of you guys would say, well, can't you use water to take the H? Yeah, we could have used water. That would have been a weak base. So there's an E1. Question. Secondary cation. Can you make secondary cations? Are they okay to make? They're okay. They're not the best tertiary. But look here. We didn't make a primary here. If you look back on the blue sheet, back up here, E2. Why E2? Bimolecular, because that's strong nucleophile. Bimolecular, it has to be bimolecular. But you can't do SN2 here. But instead, we can do bimolecular elimination. We can do E2. And E2 involves the hydroxide taking a beta hydrogen coming in here. Okay, you can do E2 with a tertiary halide. You just can't do SN2. We're not quite ready to show that product yet, so let's move back over here. Next page. Thermodynamics Entropy. We can make a look at that real quickly. Are any of these elimination reactions, are they driven by thermodynamics? Is our product more stable than the starting? You could get your calculator out, or you could just assess it by looking at what type of bonds were made and formed, broken and formed. Is it favored thermodynamically? No. You're breaking two sigma bonds. Sigma bond to bromine, sigma bond to H, and you're forming a weaker pi bond. It's not favored by thermodynamics. Is it favored by entropy? Yes. If you just get rid of the solvent, because say it doesn't do anything, if you just heat this, it'll break apart into two molecules. Not because it's driven by thermodynamics, it's driven by entropy. When you eliminate, you're breaking things apart. So your entropy term is a favorable term. Okay, regioisomers. If you do a beta elimination up here, now I'm not saying by what mechanism. Sometimes when you look at these, you could get rearrangement if you're doing carbocation chemistry. But if you just simply beta eliminate and remove the H and the leaving group, if you remove HCl, do the dehydrohalogenation, there's only one possible alkene. You put the alkene between the two carbons. But if you do a beta elimination down here, you've got beta hydrogens on two different carbons. Alpha, two beta carbons. If you take this H, and you're going to be putting the double bond in between that carbon and this carbon. There. If you take this H, you're going to be putting the double bond in here. Here. But guess what? This alkene has a stereoisomer. Stereogenic. This alkene is not stereogenic. So there's actually three possible products. Two of them being stereoisomers of each other. So we got to be able to predict which product we're going to get as major product. One above is easier. Only regioisomer, and there's no stereoisomer of that regioisomer. Which alkene will be formed? It depends on a variety of factors, including mechanism, base, orientation of groups and starting material. For example, what's the stereochemistry of the starting material? That's going to be important. Okay. Here we go. Y'all ready for this? All right. If you're not paying attention, I'd recommend you pay attention. Yeah? All right. statements here. The most substituted alkene is the thermodynamic product. That makes sense. We've said that several times before. The most substituted alkene is thermodynamically most stable. With eliminations, that's called the Zaitsev product. It gets a special name when you do elimination reactions. Zaitsev. And nobody knows how to spell Zaitsev. Some books spell it starting with a Z. Zaitsev. That's how I chose to spell it. You'll see 1,000,001 spellings. Okay? It's always a major product in an E1 elimination. And I underlined always for you. If you're doing an E1 elimination, you always get the Zaitsev product. Which is which one? The thermodynamically most stable product. So if you're doing an E1, for example, if the bottom one up there would show 3, if that was an E1, which product would be formed? The Zaitsev. Well, which one's the Zaitsev? The thermodynamically most stable. Okay, of the 3, which is the most stable? How do you judge alkene stability? Substitution. Which one's more substituted? The E or the Z. Okay, so forget the first one. Of the E and Z, which one's most stable? E. Big groups opposite. Just like conformations. Well, those can't rotate, so they're stuck there. But still, one's better than the other. Would you rather have your big groups anti or syn or anti? Yeah. E, the one labeled E, would be your product if you were doing E1. That's what this says here. All right? What if you were doing E2? You don't necessarily get the most stable when you're doing E2. E2 can often give the less substituted alkene as the most stable. And the less substituted, by the way, is called the Hofmann product. So if you're doing this reaction, what would you call this product? Any name? Yeah, it's the Hofmann product. It's the less substituted. And these two would be called the... Yeah, the Zaitsev has stereoisomers of each other. The Hofmann product has no stereoisomer. Okay, here's some examples. The above could be an example. You take this compound, heat it in water. Usually these are going to require a little heat. We can do an E1. There's no strong base here. Can't be E2. This is an E1. This thing will just eliminate. You get the alkene. Will the alkene be between carbon 1 and 2 or here? Will the alkene be down or there? Well, we're doing E1, so where do you think the double bond's going to be? More substituted. If we drew it down, we would get this alkene. Well, that ain't the most substituted. We're doing E1. It gives the most substituted. This is the most substituted. Now that alkene has no stereoisomer. If we did have stereoisomers, you would always get the E with the big groups opposite. E1 is easy. And you also created HBr. Now in this example, instead of showing HBr, I showed it ionized with water. The water is here. So there's your summary. I've already said that. What about E2? It depends on base used and stereochemistry of the starting material. For example, if you take this same substrate react it with hydroxide, we can do an E2. Since it's E2, it's concerted. We take the H, the electrons move in, we kick that off. We put in the double bond, all one concerted step. We make Br minus and we make H2O. Right here we're making H2O. This reaction will give the Zaitsev product. Basically, your Zaitsev product is preferred unless it can't be made for some reason. Your most stable alkene is preferred unless it can't be made. You can read that. When can it maybe not be made? Here's an example down below when it cannot be made. If you react this with this base, a lot different than the hydroxide. Got this stuff over here, alkyl groups, yeah? The preferred outcome here is for to abstract this hydrogen. Electrons move in, kick it off, and you get double bond here. So this is the Hoffman product. Plus your leaving group, and the other base has an H. Why do we prefer to get Hoffman here? The reason is because the base is now more sterically hindered. Compare it to hydroxide, more sterically hindered. Now the substitution is not on the oxygen, but it's over here. Well, it is on the oxygen, but then the rest of it's over there.
But H's are small, so why does it matter?
That's a good point. H's are small, and we said sterics doesn't influence acid-base chemistry. I reckon when I made that statement, I was thinking just traditional acid-base. This is really, while it's called a base and it's subtracting an H, it's really not traditional acid-base chemistry. Remember that third mechanism we said never do? That was more traditional acid-base chemistry. Question, which H is more accessible?
The bottom one.
Yes, this H is more accessible. It's on a carbon that's only bonded to one other. So, remember we did primary, secondary, tertiary? What type of H is this?
Primary.
Yeah, it's a primary hydrogen.
So even though H's are small, it's still the more accessible of the two.
Yeah, so I know we're going a little bit against the statement. I said, again, this is not just standard acid-base. What about this H? What type of hydrogen? Primary, secondary?
Tertiary.
That's tertiaries. I'll do it tertiary, okay? Primary. Tertiary. This H is more buried in there between all these carbons. The sterically hindered base, it's got the oxygen, but it also has like these wings on it. It's kind of behind it, but it's still there, okay? And it's like I want to get to you, but you've got all this stuff here, and my wings keep it. I can't get to you. Sterically hindered base is going to have a hard time abstracting the more hindered H. But guess what? If you want to make the Zaitsev product, that comes from extracting the more hindered H. Instead, it abstracts the less hindered hydrogen, the more accessible hydrogen, but that leads to the Hoffman product.
Is there less of a pull because of the sterics?
Is it less what?
Less of a pull, for polarity reasons?
I don't think that, I've never really considered less of a polarity. Mainly sterics. And you're right to say, but this is acting as a base, and you said sterics don't affect acid-base. This is not traditional acid-base. It's more of a concerted, more involved than just plain acid-base. And because it's more involved, it turns out that sterics do influence this. So, this is one reason you would not get the more stable product. And we know if you go do this in lab, you tend to get this product. This is sterics. Hydroxide is not sterically hindered. It has no trouble getting the more hidden or hydrogen, and you get the more stable product.
So it's between the sterics of the two groups trying to come together. So it's not just the sterically hindered hydrogen, but the sterically hindered oxygen as well. Trying to come
Yeah,
together.
you're right. It is both.
Okay.
Because no matter what base you use, this is still more sterically hindered than this. But if you use a small, non-hindered base, you can get that one. We're going to call this base a sterically hindered base. A sterically hindered base. Don't pull out the blue, but let me show you something in the blue. When we looked at amines before, we made a comment. Which amine is more nucleophilic? Primary, secondary, and tertiary? Primary. Tertiary means poor nucleophiles. What did we say though? Triethylamine is often used as a non-nucleophilic base. Well, we're getting to a different topic here. I didn't call it sterically hindered for E2. This is good for E2. Because it's sterically hindered. We're kind of getting into different things there, which we will clarify near the end when we start comparing substitution versus elimination. By the way, this is called the kinetic product. Is this the thermodynamic product?
No.
No, that's not the most stable. What does kinetic mean to you?
Fastest.
It's just formed faster. Why does it form faster here? Because the base can take this H faster. That's why you get the product. Not because it's more stable. It's formed faster. Why is it formed faster? Because the transition state of extracting this H is lower than the transition state of extracting this H. What makes this transition state lower in energy? Less sterics. Because if this does this, it's got to get in here in between all these groups. It's like, and that's high energy. All this interacting, that's high energy, and so the transition state is higher. Okay, another reason you can get the Hoffman or kinetic product is stereochemistry. E2 elimination has a stereochemical requirement. Okay. The leaving group and the beta hydrogen that's being extracted must be coplanar. When you're doing it in E2, by the way, you know that E1 you don't have to consider anything because E1 always gives what? E1 always gives the most stable product. So do you have to consider anything else there? No. We have options or differences with E2. Okay. One reason we just covered, because the different H subtraction. Here's another, and this is actually sort of, well, they're both just as important, but this one is kind of more comprehensive here. When you're doing an E2, the leaving group and the beta hydrogen must be what?
Coplanar.
Coplanar. Now the coplanar is sometimes called, well, hold on. With anti-coplanar, very much preferred over syn coplanar. Now, by the way, it doesn't say syn coplanar doesn't work, which a lot of students end up thinking. Just anticoplanar is highly preferred. Now, anticoplanar is often called antiperiplanar. They mean the same thing. I'm just going to use coplanar because I think it's just more plainly descriptive. If the leaving group in the beta hydrogen cannot become antiperiplanar, then the beta elimination will be very difficult. As a result, sometimes the less desirable Hoffman product is formed because the leaving group in beta hydrogen leading to that product can become antiperiplanar, while maybe they could not do so to give the Zaitsev product. You can read the rest. What is anticoplanar? Well, when we did conformations, we were doing that. Yes, anti is synonymous with trans. You use anti more often when you can rotate. Trans more when it's fixed. These would be anticoplanar. That is, the H and Br are both in the plane of the board. It's not like one's forward and one's in the plane, one's forward. That would not be planar. Planar means everything's in this plane, both in the board, but about the bond, though, they're anti. So these would be anticoplanar. Now, how do you show that in our good old Newman projection? Okay? If this is carbon 1, that's carbon 2. Carbon 1's in the front, and there's a bromine going straight up. Carbon 1's in the front, bromine going straight up. I'm not showing the other things on the front carbon. Then the back carbon, which is behind that one, yeah, H going straight down. See? This is looking from this way. The plane is here. But they're anti. So they're both in the same plane, so we call them coplanar, anti. This would be syn coplanar. And if you drew this in a Newman, these would be eclipsing each other. Okay? And syn coplanar.
Would one on a dash and one on a wedge, would that also be anticoplanar?
I'll typically put things in Newmans. Okay, what about rings? Remember our chair conformations. Which hydrogen is anticoplanar to the bromine? Well, this one. These two are anticoplanar. That is, this one is straight up. Which one is straight down? That one. These two are anticoplanar. These two are not. They're not in the same plane. Okay? Anti could also be called trans coplanar. Well, which hydrogen is trans to the bromine? It's up. That one's down. It's up compared to the H. This one's down compared to the H. These two are trans. They're also coplanar, so you could call these trans coplanar or anticoplanar. Either works. Okay. Look at this. Which hydrogen are the ones, you got beta hydrogens on both sides. Which one is trans coplanar to the bromine? Which one is trans coplanar to the bromine? None of them are. First off, trans, only that one, it's down compared to the H, it's up compared to the H, so those are the two that are trans to the bromine. So forget about the other two. But question, is either one of those coplanar to the bromine? Actually, no. You can look at a model and see. Here's a take home here. The only way to have an H anticoplanar to a leaving group on a ring like this, on a chair, is for the leaving group to be axial. If the leaving group is equatorial, none of the beta hydrogens are transcoplanar.
So anticoplanar is basically the same as E or Z, like E and syncoplanar Z.
Well, you're mixing. E and Z is a fixed conformation about double bonds. Your stereochemistry has different terminology. Largely, if you can rotate or not. Close similarities, but not exactly the same. Okay. Show the product of the first reaction. Why don't we pass back the quizzes real quick while you're looking at those. We'll see what type of questions come up with those. Okay, if you want to pick it up here, please yell. The B lab first. Troy. Here. Remy. Thomas Stringer.
Here.
Thomas Crumley.
Here.
Jake.
Here.
Jacqueline.
Here.
Catherine.
Here.
Alexandra.
Here.
Karina.
Here.
Julia.
Here.
Jacinth. Here. Victoria.
Here.
Bianca.
Here.
Armand.
Here.
Nick.
Here.
Lauren.
Here.
Kayla.
Here.
Esther.
Here.
Megan.
Here.
Kate.
Here.
Rosalind. Charlotte.
Here.
Shireen. Kim. Camber.
Here.
Brooke. Jennifer. Jonathan.
Hey.
Emily. Did you yell? Did not hear you. Rosalind? Okay, guys. Key is posted upstairs. Please make sure you don't make the same mistakes on the test or the final exam.
Duh.
First reaction here. Let's start thinking about substitution as well. Just because we're in the elimination handout doesn't mean we... Okay, is this going to be substitution or elimination? Do we have a tetrahedral carbon with a leaving group?
Yes.
Yes. So we can do either substitution or elimination. Theoretically. What are we reacting this with? Do we have a nucleophile?
Yes. Very strong.
What's the nucleophile?
Strong.
Hydroxide. Okay, we can make that ionic. By the way, this is not ionic.
That's just a solution.
That's an alcohol, like water. Water's not ionic. That's a neutral oxygen, that's an anion oxygen. It's a stronger nucleophile. So pretty much ignore your solid. But nucleophiles can also act as bases typically. So nucleophile slash base. Strong nucleophile, strong base. Okay. So is this going to be unimolecular or bimolecular? Bimolecular. The thing with the leaving group is involved in the rate determining step of all 4 reactions. The nucleophile slash base is only involved in the rate determining step of SN2 or E2. Okay, since it's strong, what do we know? What's going to, unimolecular or bimolecular? Why bimolecular? Because it's a bully. It's going to stick its nose in. I'm going to be involved. Here I come. It's going to be involved if it's strong. Try to keep me away from, try to keep me out. I'm not, okay. So, okay, it's got to be bimolecular. Okay, so is it SN2? Why not SN2? You don't do SN2 on a tertiary halide or a leaving group on a tertiary carbon. So if it ain't SN2, what is it?
E2.
E2. There you go. This is an E2 reaction. That's the same thought process that was on that 4th one on where we begin at today. That's why that one was E2. Okay, since it's E2, show the product. Is it going to be Seytsev for Hoffman? Is it automatically going to be Seytsev?
No, it's not.
No, if it was E1, it would be automatically Seytsev. But it's E2, and E2 has some various. It also has a stereochemical requirement. Okay, base. Is the base sterically hindered?
No.
Hydroxide is the least sterically hindered base you can have. You can't get any less sterically hindered than hydroxide, I don't think. No, it's not sterically hindered. Is it going to have any trouble abstracting the more hindered hydrogen which leads to the Seytsev? No, it will not. What about the stereochemical requirement? So because that, which hydrogen are we abstracting since it's not sterically hindered? Here's a good question here. Show all theoretically possible beta elimination products. Like we did on the previous example, show them all. Can you show them all? How many are there? 2. How many theoretically have you shown? 1, 2, how many? Theoretically. That is for us to consider. Now, we're only going to choose one of these, but how many do you consider? Anybody not voting? If you're not voting, please raise your hand. If you didn't vote in that question, stand up. Okay, there's 3 possible beta elimination products.
Okay, I got just.
Oh, E and P, and then
Yeah, I got 2.
Because if you
that at the end.
There's 1 there.
you've got that H and you've got
An H
an
there.
H here. We can call that HA and HB.
Uh-huh.
Don't forget about that one. Just because it's bolded, it looks like it's just a substituent. But that's alpha. Beta carbon, beta carbon.
Uh-huh.
What about this beta carbon? Doesn't have an H.
No.
So we ain't going to eliminate there.
So where's that one?
Well, there's 2 here though, because if you eliminate here, you get E and Z.
Ah.
So some of the choices could be just stereoisomers of each other. If you eliminate HA, you can get, if you draw them out, which is what the original question was to do,
Yes.
let's draw them out. If we eliminate HB, To eliminate HB, I'm pretty sure you'll get that right there. That alkene. Can you see that? We're making double bond here, and then this carbon has those two groups on it. And that alkene is not stereogenic, so there's no stereos. If you eliminate HA, we're putting a double bond in between here. Double bond there. The N carbon has what on it? A methyl and a ethyl. Do we need to show any boldness or anything? No. This carbon is now planar. It's no longer forward or back. It's now planar. It's an alkene. And the other carbon over here has what on it? A methyl and a T-butyl. Methyl and a T-butyl. But guess what? The ethyl and the T-butyl could also be cis. So we could draw it like this. And put the two methyls, okay, there's the compound. These are high priority groups. Opposite, what is that? Is this, it's E, right? And this is the same side. And these two are called the Zaitsev products. And that's called the Hoffman. Okay. If we were doing E1, which would be the product? E. There you go. It's the most stable of the three. But we're doing E2. We have a stereochemical requirement. The H and the Br have to be what orientation when the reaction takes place?
E.
Anticoplanar.
The same.
Well, let's draw this in a Newman projection. Let's draw the first carbon here. I call that 1 and then that back there 2. That's not nomenclature, that's just positioning. Look through there. Carbon 1. What's coming straight down on carbon 1? T-butyl. What's coming towards you guys on carbon 1? Methyl. It's on my left if I'm over here. Methyl. I'll draw that in. What's going behind the wall on carbon 1? Bromine to the right. Okay, let's look back carbon 2. What's going straight down on carbon 2? Methyl. It's actually eclipsed with the T-butyl. These are kind of eclipsed. I drew it a little bit to the side. What's on carbon 2 coming towards you guys? Ethyl. To my left. It's over here. It's eclipsed. And then what's going on carbon 2 to the behind? H. That's that undrawn H. Actually the one that we're going to beta eliminate. It's eclipsing the bromine actually. What's the relationship between the H and the bromine right here? Now they're eclipsing. They're eclipsing. They're both like this. They're syncoplanar. One plane right through here. You could lay a sheet of paper on my arms. But coming from the carbons, they're same side. We need the H to be that way. We can rotate the back H. We want the H to come this way. Okay? I'm rotating the back, so the bromine is still here. What's that? Methyl? And what's straight down? T-butyl? We want the H here. Now they're anticoplanar. And when the H comes here, where does this methyl go? You got two methyls, one on the front, one on the back.
No, that top doesn't.
Yeah, it's going to go here.
That's going to be the ethyl on the bottom.
And then the ethyl will be here. It has to rotate before it can eliminate. Now the concerted elimination takes place. By the way, why does it have to be anticoplanar? We didn't say this. Let's make yellow the leaving group. Here's the H. They're anticoplanar. That would be syncoplanar. Okay? The base, all concerted, E2. The base takes the H. At the same time, the electrons move in, make pi bond, and this gets kicked off. Okay? Well, look, when the base takes the H, these electrons move in. Look how they move in. How are they coming in compared to the leaving group?
Backside.
They're coming in sort of backside. If this was down here, they came in, they'd be coming in sort of, okay? It's sort of backside. Because these electrons become available, they fall in right behind there and kick off the leaving group. That's why they have to be like that. So, you can't really see it here because the two carbons are like this. But they are here. You have to trust this. You can get a model and look at it. But here they are, anticoplanar. And the reaction takes place, everything is set. The two methyls are on this same side. Because this becomes two sides. The two methyls are on the same side. The ethyl and the T-butyl are on the same side. Which one is it? Yes. You actually get this. The two methyls end up being on the same side. You can get out a model and look at this, but this is how I suggest doing it. Newman?
Why are we concerned about the H when both the major groups are on the same side? I guess I'm just confused why we're looking at the H.
Why we're looking at this H?
Yes.
Well, at the very top, we said that there's a stereochemical requirement for E2. The H and the leading group have to be anticoplanar.
So it doesn't matter what the rest of it is, and it does not.
Right. There's a requirement. What are you concerned with? These two groups being, well, that's actually an important consideration because the elimination takes place via a less preferred conformation. But this is the required conformation. And this is your SN1 product. This is your SN2 product, assuming you're using a not sterically hindered base. What would make the product on the right be favored? This would be favored, if you wanted this, how would you do the reaction? First off, would the mechanism need to be SN1 or SN2? If you wanted to make this. It better be SN2, because SN1 gives that one. Right? SN1 always, this ain't the most stable. SN1 gives the most stable. It better be SN2, but how would you make it this and not that SN2? Do what? No, weak base is going to be SN1. SN2 requires a strong base.
That H is very good.
Uh-huh. So how would you make it go this way? Use a sterically hindered base. What will a sterically hindered base have difficult doing? It'll have difficulty abstracting the tertiary hydrogen, and it will be more likely to abstract what? The primary one. So if we go back, and my question was really, if you wanted it to abstract the primary hydrogen, how would you make it happen? You use a stereochemical base. What's the issue with that statement? Is it just so amazing that it's got you? Do you not see that the stereochemically hindered base would? We said that on a previous page. The more stereochemically hindered base, the more it's going to want to abstract. The more accessible H. Y'all seem to not be getting that point or believing that point. Just misreading you, or what's the issue with that? All right.
Dr. Stevens,
Uh-huh.
before you erase, why did you write SN2? For those? I thought those were E2.
Oh, is that what's causing the problem?
That's what threw me off.
I was very,
Well, yeah, sorry. That's
Okay.
okay, I figured it out now. Sorry. E1. Okay. Sometimes I get in automatic mode and I get in the wrong mode. But ask that quicker. Say, hey, we're doing it. Okay, sorry. I know sometimes you guys think that all of a sudden this is substitution. No, this is elimination. Making double bonds. Sorry, have I been calling it substitution all the time?
No.
Can I ask one more question on that problem?
Uh-huh.
Wouldn't E1 make the least substituted?
E1 makes the least substituted?
Yeah.
No, E1 gives you the most stable product. Most stable product will be the most substituted outcome.
Okay. So E2 and the stereochemical hindered would give you the least substituted.
Back over here, why did we get the less substituted alkene? Because we used a stereochemically hindered base. That gave the less substituted alkene. If we used a regular non-stereochemically hindered base, we're able to get the more substituted alkene. Which is usually, that's your desired product, but sometimes you can't get it because if the base is too hindered, you'll start getting this as a major product. And the only thing I asked you on the other question was, what if you wanted to get the less substitute, or the less substituted? I thought you would maybe say then use a stereochemically hindered base because it I don't know if the SN2 just got you too confused. Okay, next one. Let's summarize it again. If you want the less substituted alkene using E2, what type of base would you use? Stereochemically hindered. Okay, let's move on. All right, what do we have here? We have a carbon and a leaving group, and we have a nucleophile slash base. It's a little unique. What is it? It's got a lot of wings on this thing. I mean, you know, an airplane. You know, an airplane can't just pull into a very narrow hangar because the wings will keep it from doing that. You got to have a hangar wide enough to accommodate the wings. Unless you got a blimp, then you can just. A blimp is not stereochemically hindered compared to a plane that's got these wings. Now the wings can be back here a little bit, but still. You see, this guy has got all this, and it can't get back there because you're only giving it this much room. Stereochemically hindered. I see a very stereochemically hindered nucleophile slash base. Okay. Substitution or elimination here? I think the very beginning of that was substitution discussion, and I kept going. Okay. Substitution, can you do, first off, is it unimolecular or bimolecular? Bimolecular, we got a bully, it's going to stick its nose in. I've got to be involved. Here I come. Okay? So it's either SN2 or E2. Can you do SN2 with this guy? Yeah. It's secondary. Well, here's a thing that's sort of a little bit of vagueness. The more sterically hindered this guy becomes, the more prone it's to doing elimination. Now this goes back to more acid-base. Because, which is going to be easier? First off, we have beta hydrogens here, and we have beta hydrogens here. Which is easier? To take an H, regardless of which one it is, or to come in here and do backside attack on the carbon, which is easier in terms of sterics? Taking an H is easier. Because the H is way out here accessible. For the base to get back in here, it has to position all the way through here and get closer to that carbon. So yes, taking the H's. So the more sterically hindered this becomes, the more prone it's to doing elimination. But then, once you focus in on elimination, then you say, well, of the two H's, which one is easier? The tertiary or the secondary? It's easier to take that one, it's more accessible. And if it's very sterically hindered, it's going to promote elimination, but not only that, it's going to promote taking this hydrogen. Show the product of this reaction. You lost your stereochemistry. Because no chemistry took place there, so you should not lose it. It should still be there at the end. How about that product there? By what type of mechanism? E2. E2? What do you want to call this product? Hoffman? Pretty sure Hoffman is one F and two N's. Hoffman product? Why did he give the Hoffman and not the say-so? Why are we proposing that? We've already said it. Very sterically hindered. It's going to have trouble taking the more substituted H. What about this? This has a stereoisomer. By the way, over here, we didn't do any chemistry at this carbon, so it should still be the same stereochemistry. This has a stereoisomer. Why did I draw it trans?
Yes.
Why not cis?
Because it would be less stable.
Yeah, but what's the stereochemical requirement for E2 elimination? The hydrogen and the chlorine have to be anticoplanar. Well, here's the take home. If you have two hydrogens you're dealing with, there's two here. Well, you got choice. And you can rotate, and they can both become anticoplanar. We could draw two Newmans. And then the question, remember the question earlier, but in our Newman we had two groups real close. Why did we do that? Well, what if you had an option and you had two of them were close, and then in the other Newman you had them opposite or further apart? Which would be better? Yeah, if you have a choice, here's the take home. If you have two, you really have a choice. If you have two H's, you're going to get the better alkene. The better alkene is trans. So you really don't even need to consider it. The only time we're going to consider the really complex, the Newman, is when we only had one. How many up here did we have? We only had one on that carbon. And that one had to be anticoplanar to the bromine. And no matter that the groups were like that, you have a choice here. There's your product. Then I'm showing Hoffman. What if the test question gave you this and just plainly told you to draw the Zaitsev product? Maybe that's the minor product, I don't know. But the question is, okay, do that. Draw the Zaitsev product here. What would it look like? You have Zaitsev? So you're saying it's going to be E? Will it? I'm not sure, I'm going to have to look at it. How did you get E?
I put the large groups trying to see each other.
What?
So that's the more stable configuration.
Do you always get the most stable with E2? Did you make sure that it was the H and the chlorine were anticoplanar?
Yes.
Because if there's only one H, you got to make sure that when it eliminates, they're anticoplanar. Anybody got it over here? Yeah, take your time, draw the Newman, see if we can get this. What is the Zaitsev product here? Just to make sure, which H are we looking to remove to make the Zaitsev product?
I drew that one. I drew out the Newman.
This H here?
Yeah.
Removing that H, we put the double bond here, and that would be tri-substituted. Hopefully you can see that. There's only one H. You got to make sure that H and the... Somebody have it? Okay, let's see if that's right. Okay, let's draw this in a Newman because I recommend that's the best way to look at it. What if I stand over here, look through here, first carbon. What's coming straight down? Methyl. H is coming towards you guys. And the ethyl is going back. So if I'm over here, that's to my left. Okay, let's look. Carbon 2. What's coming straight down? Ethyl. It's actually eclipsed. Coming towards you guys, my right is the chlorine. It's actually eclipsed with the H. There's really right in front of each other. And then, what else is on this carbon? There's an H going to the left. Please don't get your H's confused. Which H is this? Let's just call it HA, the other one HB. That's on the front carbon. It's this one, yeah? Not that one. We're not abstracting that H ever. That's an alpha hydrogen. That's on the alpha carbon. Okay. The H and the chlorine are in the same plane. I can hold up a sheet of paper here. They're cliffs, so they're right in front of each other, but they're both that way. They're syncoplanar. That's not preferred. Anticoplanar is highly preferred. We want this H to be here, so let's kind of rotate it around. Make the H here, HA. That's going to make the ethyl, no, it's going to make the methyl go up. It's going to make, everything's going opposite. H is coming here, this is rotating around here. Is that the front carbon? Yeah. The back carbon, we have chlorine.
The other ethyl right next.
Ethyl here. The back carbon did not rotate. We did not, and what's here? H? Okay. When we eliminate through there anticoplanar. The two ethyls are on the same side. On the other side is the methyl and the H. So here we go. We're going to have a double bond there. On this carbon we have an ethyl and an undrawn H. On this carbon we have an ethyl and a methyl. But the ethyls are going to be on the same side and the methyl is going to be there. And this is our Sates-F product, however you want to spell that. It will actually be the ethyls, the two main groups on the same side, Z. Because we meet the stereochemical requirements. It's highly preferred, even though the ethyls are right next to each other in this conformation that the reaction takes place in. Highly preferred means this is preferred to happen as opposed to these being opposite. Since this is a miraculously stereoclahedral base, we're going to probably get the Hoffman as the major product. But that would be the Sates. Now, what if you did this by an E1? Which of the two up here would you get if you did E1? Or would it be neither of these? It would be neither. So if this was an E1, what would you get?
The E.
You get the Sates-F E, because that would be the most stable of any you could draw. What would you react this with instead of this to do an E1? Instead of this, what would you react it with instead of that?
OH.
What do you mean OH?
Like maybe KOH or something.
A strong?
A strong base.
No. KOH would give you this product. Because KOH would be E2. E2 Sates-F is this. It has to go by anticoplanar.
What about water?
You would not want a strong base, you would want a
Weak base.
weak base. Like just heat this in water. Problem is that's not a good setup because this ain't going to be soluble in water. Maybe just heat it in ethanol. You really, remember the early one we had no solvent at all? You could just heat this by itself? Because if you, what is an E1? Ionize, and then something takes the H. What could take the H? The Cl minus could come back and take the H. You really don't need anything at all. In practice, you'd probably just heat it in some solvent, like ethanol, BE1. Okay, how about a ring? TEA is triethylamine. Triethylamine, say. Strong base, weak base?
Strong base.
Yeah. Now it's not super strong, but we do classify it as strong. THF is just a common solvent. Tetrahydrofuran. Okay. Substitution or elimination? Why elimination? Because what?
It's highly substituted.
Highly substituted.
Living on base.
And substitutions are worse influenced by sterics.
Yeah.
And actually, this is where I can show you again. When we had the blue. It is right here. Triethylamine. TEA. Often used as a non-nucleophilic base, such as for E2 reactions. Much better nucleophile. Sterics makes nucleophile not good. Poor nucleophile. Much better as a base. For like E2. Strong E2. Now the question is this. Are we going to get Seytzeff for Hoffman? Well, this is kind of a little gray area because how sterically hindered is it? The more sterically hindered, the more prone we're going to get Hoffman. But when do we cross the line? That's why a lot of times some of these questions, maybe you're asked, give both. Show both the Hoffman and the Seytzeff product here. And then maybe try to think which would be preferred. But again, that answer is going to be difficult. Show both the Hoffman and the Seytzeff. Now that I look at this further, I kind of see I see something here. There's only one product going to be formed here. Only one product going to be formed. That alkene is your product.
So you can't form.
You should be able to, and that is that Seytzeff or Hoffman? Hoffman up here. Yes, that's the only product here.
Why?
Why? Okay, to get the Seytzeff, you would have to remove
That one.
that hydrogen.
Yeah,
What's wrong with
yes.
Is that hydrogen trans or anticoplanar to the leaving group? No. Transcoplanar? They have to be trans. Is the I and the H trans?
No, there's
So they're cis. Since they're cis, they will never be transcoplanar.
Because they're in the ring.
So if it was
Can't rotate in a ring. Now I could, maybe theoretically you could still draw it, but that's, because it's that bad, we don't even consider it a theoretical product. There's your product there, that there should be, so See, I was looking at, well, is this sterically hindered so much that it's going to take that and it can't take this? I didn't consider